Hello and welcome to the second video of chapter 3. All right, so we're continuing our discussion of classical mechanics, and here we're going to talk about throwing a ball downward, or maybe a more general description is we are in section 3 of chapter 3 because the first two sections were covered in the first video. And so in this video we're going to talk about 3.3, beyond freefall, throwing a ball upward. Okay? And we'll also talk about throwing a ball downward, which I don't think has its own section, and the next one's going to be projectile motion. All right, and we'll not cover projectile motion in this video. That'll be in the next one. Okay, so we're just going to focus on this idea that we understand that a free fall object or an object in free fall is experiencing one and only one acceleration. Okay, that acceleration is expressed by a generally, but because we're on Earth, we call it g for 9.8 meters per second squared. Okay, so that's going to be kind of our starting point. And to elaborate on that, let's head over to the tablet so I can write a little bit about what I mean real fast. Okay. Okay, so sometimes there's just no substitution for writing it down and getting a good idea here. So what I'm talking about is that we have our equations of motion. Okay, so these are going to be the equations of motion for constant acceleration. Okay, do you remember what those are? Okay, there's really two of them that we've seen so far, two special equations that we're going to be expected to work with for constant acceleration. One of them was velocity, so it gives us instantaneous velocity over time, and it's linear, and it has the initial velocity v naught built into it, and then just some acceleration. Okay, it's always a diagonal line, it's linear. Okay, it can be angled up in the case where the velocity is growing and the direction of acceleration is in agreement with the velocity, especially the initial velocity. It can be pointed downwards. The initial velocity is simply going to be the vertical axis. You get the idea. Okay, the other equation was the one for position. All right, I'm gonna write here in terms of x. All right, and here we would just have v naught t, and then plus 1/2 a t squared. So a little more complicated. Two terms of t, one's a t squared. If we were actually asked to solve for t and there was no zeros here, in other words, the initial velocity was not zero, which is kind of the focus here, right, in this beyond free fall, all right? Well, in those cases, solving for t actually does require that we use the quadratic formula, okay? I'd rarely ask that of you. I don't know of any homework problems that do if you're in my class, but it is something to be aware of, okay? So that's generally for constant acceleration. So specifically for gravity, right? So for free fall, a is not just some acceleration, it's always going to be equal to g, and we're going to call that negative 9.8. Okay, meters per second squared. Hopefully we're familiar with those units. Why negative? Because I'm basing everything off of the following coordinate system, which is definitely the more typical one, so I don't think you'll have an issue with this. All I'm saying is that we have x equals 0 on the ground, okay? And then above that, we are measuring positive x in the upward direction, okay? So this is in the direction of positive x, all right? Furthermore, we have an idea that gravity must point downwards, therefore it's negative. So if I put it over here in purple, this is the vector of gravity. All right, pointing down, hence the negative, because we're just being consistent with our one-dimensional coordinate system, okay, which is just like a number line, right? I'm just saying positive x is this way, negative x is the other way, okay? Except, of course, I'm actually not going to use x. On these problems, I'm all going to use y, okay? Because it's, after all, a vertical system, and we tend to use y for vertical systems, okay? That doesn't change the value that a is now set to g, which is numerically negative 9.8, okay? That means that our equations of motion now are going to be Vy, because we only care about the y direction of motion, equals V naught y, and then minus gt, okay? All right. Now here, if I put minus and I plug the negative in, that would be double counting, right? So think of it here as that I took the negative out of the g, right? But I want to highlight the negative, so I'm going to leave it here in the equation. I think that's easier to read. All right, and over here, the instantaneous position, vertical position y, is just going to be v naught y times t minus 1/2 gt squared. Okay, so those are the equations of free fall. All right, and that's all generally free fall. All right, your textbook understandably calls some cases beyond free fall, and those are the ones wherever v naught is not equal to 0. Okay, so in the language of your book, right, the language of the textbook, if v naught is equal to 0, and these equations simplify, where vy just equals negative gt, and y just equals negative 1/2 gt squared, right? Those simplified versions of the equation, both when the initial velocity is equal to 0, that's simple free fall, okay? And that was section 3.2, previous video, all right? But here we have a case where we can extend this concept and talk about any initial velocity, okay? So like in the picture, we can imagine an initial velocity of up, right? So this is a girl throwing something straight up, right? It's gonna reach some maximum height and then come straight back down, all right? In this case, we show a little bit of 2D motion, so it avoids our hand and we can actually see it, but we assume this is one-dimensional, right? Straight up, reaches some maximum point, right? At that moment, it's momentarily at rest and it comes back down, all right? And when that all can be worked out of none other than the two equations, right? So they completely describe that system. They can tell you things like how high that maximum point is, okay? How much time it takes to get there, and so on. Okay? So, if the ball is thrown upwards, right, gravitational acceleration is still directed always downward, okay? That hasn't changed. So it's still free fall, right? It just starts moving up, but of course slowing down. Here the acceleration is in opposition, or is the opposite direction of the original upward velocity, hence the slowing down. Okay, so consider a case here. We'll do another case. We'll work out the numbers and I'll ask you to try it at home. Let the initial velocity be 20 meters per second upwards, right? So this was someone throwing something very quickly upwards, right? They're launching it upwards. All right, so immediately starts experiencing a downward acceleration. From the moment it's airborne, from the moment it leaves the person's hand, right? Shown in the picture, the figure. Well, in that case, right, from that instant on, the only acceleration that's acting on it is because of the only force acting on it, which is gravity, thus gravitational acceleration, okay? And if we round that value to 10 meters per second, all right? And that should be meters per second squared, right? Because it says, let's see, immediately starts experiencing a downward acceleration due to gravity of approximately 10 meters per second squared, okay? So it is a typo in the publisher slides. Here it's actually correct to say that the velocity is changing by 10 meters per second because they're talking about that rate of change, all right? So they actually are talking about velocity in the second bullet point, but the first one should be squared, okay? But what it says that every second the velocity decreases, okay, at 10 meters per second. That's always true, okay? Well, although it's not always a decrease, right? But there's always a change of 10. When we just drop something, in the simple case of free fall, drop it from rest, v naught equals 0, it picks up speed as it falls, okay, in the absence of air resistance, and it's going 10 meters per second faster every single second that it's been in free fall, right? So here, the same idea of 10 meters per second change in velocity every second, that's what the acceleration means, rounded to 10, okay, meters per second squared. But when there's that initial upward velocity and this perfectly vertical toss, well, it results in a slowing down. Of course it does, right? Because it's that opposition between the vectors. We can see it here, right? So we're starting off the clock at t equals 0. We're calling d equals 0 as well. That's what I would call y equals 0. That's just our initial benchmark position. And look what is not 0, v, right? v naught, you could also label this variable here, is definitely not 0. In fact, it's 20 meters per second with the positive denoting upward, right? Just like in my figure, we're defining upward as positive, okay? So after the first second, the ball has traveled, right? How far? 15 meters. We can solve for that. Okay, that's pretty cool. It might not be immediately evident, but we plug in to the equation, right? We literally plug into the lower equation, the one that I was writing, right? But of course with the appropriate signs and replacing a with g, and we can just solve for how fast, or rather in this case, how high it is after 1 second of motion, okay? And the answer you get is 15, okay? Now what's interesting is it slowed down, okay? It's experienced that gravitational acceleration the whole time, right? That's never gonna change. And it slowed down from the initial 20 upward meters per second to 10 upward meters per second, okay? Now, check it out. It reaches the top, it's still slowing down at that same rate, right? And since we're rounding everything, it takes exactly 2 seconds, based on our rounded value, for the velocity to have slowed down from 20 meters per second upward to 0, right? Because it's slowing down 10 meters per second, okay? That's the pinnacle, that's the peak, right? And so that's one way you can solve for the peak. is you can just set the instantaneous velocity to 0, because you know that's always the case at the peak, because it is changing, right? The velocity is changing from one sign to the other. So if we were to look at it graphically, it would be crossing over the horizontal axis, all right? That means it must cross through the numerical value of 0, all right? Which means physically it's going to be momentarily at rest, right? Top, come back down, all right? Now, notice, as I said, one thing that hasn't changed the whole time is that the acceleration is just gravity, right? Unchanging. That's the whole deal with it being constant and uniform, right? Okay, well now continuing, after 3 seconds, we have a case that you might have expected because it's going to be symmetric, right? That's the case. With this constant acceleration, there is total symmetry. So now, just as much time as it took for the ball to slow down, right, and then reach that momentary point of rest, and then come back down, well, it gets it gets 1 more second and it's back to where it started. Okay, and then after 2 more seconds, it's now back to the exact height where it was released from. Now again, we're showing a little bit of horizontal motion so it doesn't hit the person's hand. And we're also, what's fun to imagine with these is we put our person on the edge of a cliff, so then we could actually continue the motion of the ball, and it would just become a ball that it would be effectively thrown downwards, right? Because we would start at 0, right? We would define d equals 0 because the ball is passing back through it, okay? And then, but since it's definitely does not have a 0 velocity at that moment when it's passing through d equals 0, or what I would call y equals 0, well, that means that it's, like I said, it's effectively thrown downwards. It's still going to be accelerating at g, right? But it's going to have an initial velocity of 20 meters per second down, okay? So in other words, it would actually hit the ground sooner, okay? Sooner than something that would be, dropped. Okay, because it takes less time for it to cover that distance because it has that advantage of the initial velocity. Okay. All right. So, all right. There's the same picture. There is some videos within the text that explain the different cases here, right? Or rather, tracking it over time and plugging into the equations and really kind of putting the equations through their paces, right? Getting some use with them. Here is none other than this kind of the showing that velocity. You know how I mentioned that the ball reaches some point, that's that high point, and we could solve for the time it takes to get to that high point because we'd simply set the instantaneous velocity at the high point equal to 0, right? Because I said it's changing direction, right? It's going from positive velocity to negative velocity. It has to cross the horizontal axis. And there we see it, right? Crossing the horizontal axis at 2 seconds, right? Indeed, having a momentary and instantaneous value of v equals 0, right? At that instant. The instant it turns around, okay? And then speed, by the way, is just the absolute value of this, right? So it would have all the same slopes, but it doesn't go into the negative, right? So the speed ends up with this weird effect where it gets kinked because you're essentially just reflecting this portion of the linear graph back up into the positive, right? Because that's how speed is calculated if you were to know velocity first, Okay. All right, let's look at a couple more slides. All right, so, all right, I already talked about the question here. Sorry if I gave it away, but just the idea is that the acceleration was unchanging, but we got more, okay? All right, so the velocity versus time plot, okay, it's shown here, starts at 20 meters per second, okay, as we spoke about, so it's positive, and it decreases, crosses to that 0 point. So this is the graphical representation of what the figure was showing us, all right? And then it just continues downwards. So it's the same slope the whole way. And what is the slope? What is the meaning of the slope of this velocity versus time graph? Right? Think rise over run, the units of rise over run, it's meters per second, it is acceleration. Okay? And since this is a linear, function here, that slope doesn't change, it's just one value, right? Okay. And in this case, it's negative 10, right? My case is usually be negative 9.8. Okay? So in the next video, we'll talk about projectile motion, but to finish this one up, let's do some more examples. Okay, so just thinking about these cases of really kind of like we'll stick to standing on flat ground. Unless we're going to launch something downwards. Okay, but let's start by just tossing it up because that's what we saw. So this is considering someone that's standing on flat ground and they're going to throw something up, and we're just going to answer a couple of questions about what is the behavior of that object experiencing only a gravitational acceleration while it's in the air after being thrown up. Okay, well, tossed upward. Okay, so where do we want to put this? Right, we're definitely going to want the equations in our box. I'm going to make it a fresh page for us all. Okay, So let's go ahead and call this example. Okay, and I will include a picture. All right, so we'll have a object of some sort, round object. I'm not going to draw a person or anything. Not a very good artist to draw a person. Also, let's just imagine that something's launching it. It doesn't really matter what it is, but it's it was launched in some way, maybe a big spring or something, and it has some initial velocity. All right, so that's going to be its v naught. I'm going to give it an initial velocity of, let's make it pretty fast, 38 meters per second. Remember, that's like 100 miles per hour or something, right? So it really is, it's being launched. Okay, same coordinate system, positive y is upward, okay, which means that by definition, gravity is going to be negative, okay. Also worth noting, we're going to use 9.8, not 10, okay, meters per second squared, units of gravity, and obviously that gravity is going to oppose the initial velocity, so we're going to have that same slowing down motion. What we should absolutely expect here, in a faint dotted line, is that our object should come up to some maximum point, turn around, and then come back down. Okay? So that's going to be the type of motion that we're going to be able to solve for. Okay? All right. So let's have, I want to see what, there's so many different ways we can take this. The one we saw asked a question about, what was the acceleration? It's unchanging, right? So I won't ask you a concept question like the one we saw on the slides. But I'd rather ask you a numerical question. So put out and say, what's something that we can solve for in the system? Okay. Well, let's just find out where and how fast it's located at a certain time. That's it. Okay. So, all right. So the question here is, all right, what is the position and velocity of the object at t equals, let's think about this, I'm going to have it be 5 seconds. There's some behind the scenes reasons that that's a good time, okay? So 5 seconds in the air, 5 seconds after it was launched, 5 seconds of only experiencing a acceleration of 9.8 meters per second squared directed downwards. What do you got? You're going to use these equations, okay? And you just want to solve for position and velocity. So you can think what you're finding is you're finding, y, and you're finding v sub y, okay? You shouldn't have to do any unit conversions because the velocity is in meters per second. Excuse me. The time is in seconds, and the acceleration is given as meters per second squared. So you're all in the same, what are called base units. No powers of 10 or anything here. All right, certainly no conversions over to the metric system. So plug in as written into the equation, give it a try, pause the video. All right, everyone had a chance to do it. Let's now quickly talk about the solution here, okay? So I consider this a straightforward version of this problem because we are just plugging in the time, really putting it to use. Now interpreting the answer, making sure it makes sense is a great next step here, which we'll talk about briefly, okay? So what is y going to be? The instantaneous position of the object at 5 seconds, right? Well, one thing which I kind of implied in previous problems but didn't outright say is that we're starting at y equals 0, right? The ground is y equals 0. So everything is measured relative to that. As I said, that's pretty much what we're sticking to, right? Wherever our system starts, that is our 0 point in terms of position. Okay? So then are you going to expect a position that's going to be positive or negative? Well, better be positive because there was no mention of standing on the edge of a cliff, so we shouldn't expect the object to be below where it started. It's not a case where we're dropping something off the edge. So we should get something positive. If I gave you too large of a value of time, if I gave you 500 seconds, for example, well then it would have already returned back to where it started. In this case, that means it would have just landed back on the ground, right? Now, were we on the edge of a cliff, I could then give you much longer times, much larger times, although of course they would eventually become too large to become reasonable as well, okay? In terms of, thousands of kilometers, well, you're not going to be able to drop something thousands of kilometers, would you, okay? Cliffs tend to be just 3 or 4 kilometers at the absolute highest limit. All right, so plug this in. We're doing position first, which is a longer formula, but the more fundamental idea. Okay, so we'll just plug in the 38 meters per second over here. We'll multiply by that time that was given, 5 seconds. Remember to subtract 1/2 times 9.8, okay, 5 seconds. Quantity right there, and then remember to square the 5 seconds. Okay, so you don't square in the first term, but you do square in the second one, all right? And I'm putting units on everything, but I was dropping them from the acceleration, so I'm putting them in here as well. Okay, so in the calculator, what would this look like? All right, so what we'd plug in, and you could, by the way, if you're using Desmos, you can actually label your variables. I could call this H or something if I'm going to do something with it, make a calculation later. But here I'm just going to have 38. I'll multiply by that 5, and then I'm going to subtract the 0.5 times 9.8 times 5 squared. Okay, so we get a height of 67.5. The instantaneous height of the object after 5 seconds of being airborne is in free fall, right? 67.5 meters. Okay. What about the velocity at that moment? Well, what do you think, right? So if we captured it on the way up, you know, if the 5 seconds is before it's got to its high point, right, before it's turned around and is heading back down, then the velocity that we should expect to solve for will be positive. If 5 seconds actually represents the point where it's already heading back down, then we should expect our velocity to be negative. So which should we expect then? Do you have an idea for it? Okay. Well, solve for it if you haven't already, and see what sign you get, and then ask yourself if it makes sense. Okay? All right. Here's the solution. So what we're going to do then is we will just plug in to the equation on the top, all right, to find the instantaneous vertical velocity, in this case the only velocity in town, since it's just one-dimensional. And then we'll plug in our initial of 38 meters per second, and then we'll subtract 9.8 meters per second squared, no half in this formula, okay, and then just multiply it by the 5 seconds. So what do you see already? All right, what does it look like is happening here? All right, we'll just call this V. Okay, so I have 38 minus 9.8 times 5. Well, 9.8 times 5 is, you know, close to 50. So we have, you know, something that's close to 40, 38 minus something that's close to 50, right? So it looks like we're going to get in the negative range. And indeed, I chose those values because I thought about the fact, one easy thing to remember is that, you know, any object that's thrown upwards, when it's only experiencing gravitational force, and thus gravitational acceleration, slows down at the rate of 10 meters per second per second. So when I look here, I'm like, oh, well, if I'm throwing it upward at a rate of 38 meters per second, that means it's going to take, you know, just under 4 seconds for it to slow down to 0 at the moment that it turns around and starts falling back down. Okay? So then I knew by asking for, you know, the position and velocity after 5 seconds, I would be capturing a moment when it's on its way back down but hasn't hit the ground yet. Okay? Because it's going to take as much time as it took going up, exactly as much time to go back down. Okay? So what we had then is we're going to have the value negative 11. Okay? Meters per second. So if we were to draw that, that would be a vector pointing downwards, right? So that's the instantaneous velocity at that moment. Okay? So, you know, maybe somewhere up here, right? That's where it's located at this moment. Put our blue object up there, right? So some point, and then I'm saying that it has, you know, some velocity at that moment, right, of negative 11, right, pointing down, okay? Now, what's especially interesting is I drew it, kind of thinking about this, is that, you know, clearly it's on its way back down. The value we got definitely was not 0, you know, the velocity we solved for. So this is not the high point, is it? What if I actually wanted to find out the height that the ball reaches, the maximum height it reaches? Well, that's a common question, right? So let's ask it and answer it. So part C, what maximum height does the object, called a ball sometimes, reach? Okay? So think about what we know here, right? We know that we captured it at 5 seconds, which was an arbitrary choice, right? Kind of in a sense, like other than me choosing kind of where it was going to fall. But at 5 seconds, no special number for this motion. Well, we know we captured it on its way down, okay? We captured it going fairly slow, so kind of close to the top. And by fairly slow, I'm just saying that negative 11 is a lot. You know, it's definitely not almost all the way back down, because at the moment it's about to hit the ground on its way back down, it's going to be going negative 38, right? Because it would sped back up to where it started. And by the way, that all falls nicely into ideas of like conservation of energy, right? Gave up just as much kinetic energy on the way up as it gets back on the way down, all right? So more on that in a later chapter. Okay, not much later, but later. So okay, so we're going to be kind of, you know, maybe over halfway or something, right? We're definitely, you know, up in the upper half of the toss as I sketched it here, right, as I showed it. So okay, and that tells us then that the 65.5 definitely is not the maximum height, and whatever value we solve for in this part C is going to be bigger than 67.5, right? Okay. So how do we actually solve for it? Well, as I said, it's pretty simple, right? And you know, you still have to use an equation and rearrange some things, but as far as an equation to rearrange, you couldn't ask for a simpler one. And that's you're just going to set the instantaneous velocity equal to 0, because that is the velocity at the top, right? And then just solve for t from this equation here. Okay? So what that would look like in practice is we would write 0, which has replaced v sub y, the vertical velocity, equals 38 meters per second, the initial velocity, minus 9.8 meters per second squared. So, you know, just like this equation up here, right? But here we were solving for v sub y. This time we set v sub y to 0, right? So instead we're going to solve our variable, our unknown, is going to be, you guessed it, t, right? Because we're finding the time. But we didn't ask for the height. Yeah, but you have to do this as 2 steps, okay? Because at least if you don't want to, you know, use the quadratic formula, because once we have the time, then we can plug the time into the position function. So I'll show you exactly what I mean. All right. So here the time that we're going to get is just going to be negative 38 meters per second divided by negative 9.8 meters per second. Okay, that's because I would have had to subtract 38 from both sides of the equation, and then I'm just dividing both sides by the entire, you know, coefficient in front of t, the entire value attached to t, which has a negative, okay? That's important because the negatives cancel out, as they should. When you should never solve for a negative time, okay? So over here, I'll just call this t. And this one, actually, I will be plugging it back in, so it's helpful to label it as a variable if you're using Desmos. And it's just going to be 38 divided by 9.8, okay? 9.8. So 3.88 is the rounded value, and essentially I'm saving the unrounded value within the calculator, and that's seconds, okay? That totally is consistent with the 5 seconds, because the 5 seconds was already on its way back down, okay? Well, at exactly, or rounded to, you know, the millisecond place or the hundredth of a second place, 3.88 seconds is the moment where it's at the top, okay? Momentarily at rest. All right, so then we just plug that into the position in order to find the maximum height. So we'll call this y max, the maximum height it reaches, right? That would be none other than this value right here. All right, so this entire length would be y max, okay, as I drew it in the sketch, because that's where it turns around and comes back down. And then we'll plug in everything in our y equation, which is just the 38, okay, meters per second. We're going to plug in the time we solve for, so the 3.88 seconds. If you plug it in rounded, that's okay, but it can affect your values because you're essentially then going to get an answer that continues to get more different the more times you plug in rounded values. All right, so you don't want to do that if you can avoid it, and using a program like Desmos makes it easy to avoid. Okay, so 9.8 meters per second squared, and then multiplied by that 3.88. Don't forget to square it. Okay, so finally then I'm going to solve for this. We'll call this uppercase H, right? So for big H, big height, the max height, that is. And we'll just take the 38, okay, we'll multiply by t, which I have saved as 3.88, right, approximately, minus 0.5 times 9.8, and then times t, don't forget to square it. 73.7, again rounded, not meters per second, but meters. Okay, so that right there is our answer to part C, the maximum height that it reaches, indeed where we expected it to be, so there's no obvious calculator numerical mistake we made, because it's bigger than 67.5, right, as it should be, right, because 67.5 is on its way back down. Okay, so you know, a few extra meters above that point, that's the highest it gets. Okay, if you want to get it higher, well, you could go to a planet with less gravity, so you could just have a different value of g, something smaller than 9.8, or you could just give it a greater initial velocity. And let's take a quick look at that. Let's look at an example here of something that's in free fall. Let's go ahead and let's restart. All right. So here we're just dropping something. All right. But I can give it an initial velocity. All right. So here it's just going to fall down and hit the ground. All right. So let's go ahead and reset it. I'm not going to start it yet because I'm going to give it an initial height of 0, kind of like in our examples, and let's have it go up. All right, so I'm going to give it an initial velocity as big as we can of 20. And look, it started the simulation. There it goes. It's going to reach some maximum height. like in this case, the maximum height using their value of 10, right? Look, you can see even in the graph, right? We could solve for it more exactly, but in the graph it's going to come out as 20. See, that was the maximum height. Notice that the position is a parabola, really nice parabola because we got both sides of it because that's on the way up and then on the way back down. The velocity is linear and it passes through 0 just as we expect. And the acceleration is constant, and it's just a constant value of negative 9.8. And, or in this case, negative 10 exactly. Let's make this a little bit, there we go, 9.8, the value I like to use. So I'll change it ever so slightly. And again, you know, if you wanted it to reach a greater height, right? In this case, we maxed out our initial velocity. So the only thing I could do to this system to, you know, actually make it have a greater height would be to make the acceleration less. So imagine we go to the moon or something where the acceleration from gravity is only 2, you know, or around that, 2.4, we'll say, meters per second. Well, how high is it going to get this time? Well, much higher, right? Look, it has no problem. At first, it almost looks like the position is linear because it's just, you know, there's a lot less of a downward acceleration. There's a lot less effect from the gravitational force. But clearly it is, you know, topping out. Everything is also slowed down, so you know we're measuring time at the same rate. So the simulation looks like it's running slower because it's just taking longer to go through this whole process with the smaller acceleration. All right. So you know not only can you jump to a greater height on the moon with the same amount of force, okay, you also the whole process would seem like it's moving in slow motion. All right. And then eventually it will eventually come back down and speed up all the way, coming back down. Okay. I think we can actually mess with it mid-simulation, see? No, that actually resets it each time. So here's a value that's a little bit less than Hertz. Okay, all right, and hopefully you get that idea. I guess one other thing is that I mentioned throwing something off the edge. So you can imagine starting at a height and actually giving the object a initial negative velocity, right? So here you're not just dropping it, you're throwing it down. It's still going to accelerate, right? So you can see here the initial velocity was some value. Maybe negative 17, I'm looking over at this part of the graph, and the effect of gravity still causes it to speed up in terms of falling more quickly, but you still gave it a big initial burst by giving it a large downward initial velocity. Okay, that wouldn't work on flat ground because we just hit the ground, but another case, another example. Okay, so I hope this really kind of starts giving us a set of tools and an approach and a perspective of how to solve these problems that have motion in them. It all comes down to equations like the ones that I've called attention to, right? There's just a few simple equations that describe motion. There's only a few types of motion that we are focusing on in this class. Constant acceleration motion is one of them, right? And it's part of a select group. And as far as our continued discussion of constant acceleration motion, all we're going to do in the last lecture to wrap up this chapter, all I'm going to do is talk about projectile motion. And projectile motion is literally just this, what we've been doing, but adding some constant velocity side motion on top of it. Because when you look at a projectile, like launching a cannon, right, and seeing something fly off the edge, right, getting that characteristic parabolic looking motion through space, well, what's happening is if you were to graph the position of the vertical position and the horizontal position over time, you'll see that the vertical position is exactly like it was for free fall, for one-dimensional motion. It's unaffected by the horizontal motion. We say they're uncoupled. They don't affect each other, horizontal motion and vertical motion. So then mathematically, we solve for it no differently. We just then might plug back in a time, like I did in my example, in this case to find a maximum height, we might plug a time that we solved for back in to find out maybe a maximum range. Like something like in this picture here, how far does the ball roll off the table depending on how fast it was going when it left the edge? Those are the types of questions that we can answer by considering motion in the vertical direction and motion in the horizontal direction separately from each other, which makes the whole approach much easier, and it makes it exactly like what you just saw in this video. Okay, just plus one more step. All right, so hopefully you'll stay tuned for that. Hopefully that sounds interesting. Thank you so much for watching this video on free fall. I hope it has been interesting and informative. Bye for now.